And welcome to this last video of the series Basics of Linear Algebra for Quantum Mechanics. And in this video, we will see some of the more and other relevant linear algebra concepts, which will be very useful for you to understand the quantum mechanical concepts later on. To begin with, we have something called as Kronecker products. And what it does is that it do a representation of a composite system, which is combination of two different vectors. It's represented by a cross in a circle, as you can see on the screen. So for example, if you have two systems represented by vectors A, B, and C, D, it can be represented in a Kronecker product by multiplying the first element of the first vector with both the whole second vector, and then taking the element-wise product. As you can see in the example, this results in A multiplied by C, A multiplied by D, B multiplied by C, and B multiplied by D. If you want to understand this concept in a more layman terminology, so for example, if the first system represents that we have a cake and ice cream, and the second system represents flavors of that, chocolate or vanilla, you make a composite system out of this, and you will end up having combination of cake chocolate, vanilla chocolate, ice cream chocolate, and a vanilla ice cream. The same concept can be extended to matrices, which represent a composite system represented by two individual matrices. The rules remain the same. It's just that now you have to multiply each element with the second matrix, each element of the first matrices to the whole second matrices, and then expand the multiplication element wise. If you see the example here, the two matrices represented by different elements having the same dimension resulted in a bigger matrices of the bigger dimension. So 2 rows and 2 column matrices are now represented as a composite system of 4 rows and 4 columns. An important rule for the Kronecker product is to remember that if A is a Kronecker product with B and C is a Kronecker product with D, then A and C are Kronecker product with B and D. Sorry for the pronunciation. These concepts will also help you to understand something called as eigenset and eigenvector. Now, in terms of eigenset, the matrix vector or a scalar vector surprisingly gives the same result. Look at the example here. You have an old matrices represented by element 2, 2, and it is multiplied by a matrix. Sorry, you have an old vector represented by 2, 2. Sorry for that. Multiplied by a matrix and gives you a new matrices represented by 1, 1. And if you apply the same scalar product or a number 1 by 2 to the old vector represented by 2, 2, it will give you 1 on 1, which means the scalar and the matrix multiplication will end up giving you the same result, which can then be extended to a definition. And what it says is that for some special vectors, there are special scalars that mimic the matrix. For example, if you have a vector x multiplied by a matrix A, which is also represented by same scalar like lambda for those vectors and a scalar, they will end up being called as an eigenset, which means they are composed of eigenvalues and corresponding vectors representing those values. If you look at the deep example of it, especially in 2D, you have a vector represented by element x1 and x2 multiplied by matrices represented by a, b, c, d, and the same vector represented by x1 and x2 is multiplied by lambda, a scalar. If you expand this mathematically and rewrite this equation, making the right side as a vector of represented by 0, 0, you will end up in the last equation. Now you can solve this equation using the determinant approach of matrices, and you will end up finding the last equation, which will be of type a minus lambda, d minus lambda, minus bc is equal to 0. So you will have to solve this using the basic linear algebraic mathematics. You may end up then in eigenvalues of lambda 1 and lambda 2, as we have seen in the last equation, which each eigenvalue have a corresponding eigenvector x, as shown in the example here. It is important to understand in terms of the Hermitian matrices that if an matrices and the conjugate of the matrix is the same, then it's Hermitian. Then such an Hermitian matrices has a real eigenvalues, and it is comprised of linearly independent eigenvectors, which mean the component vector do not have overlapping relationship with each other. It has to be noted though that the eigenvalue need not be distinct. They will still end up representing distinct vectors. To summarize this whole series, the take-home message is that you must understand the basics of complex numbers, understand the vectors, what are the norms, how to operate on inner product and the linear independency, matrices, which are the tools for manipulating the vectors, what are the different kind of matrices, like a square, Hermitian, identity, and unitary matrices. And then you have to understand the concepts of linear algebra like eigensets, or the tensor product, or the Kronecker product that is also called. We have not used the word tensor product, but Kronecker products are called tensor products, which will help you to build complex system from individual components. This is it about the basics of linear algebra for understanding the quantum mechanics. I hope you have enjoyed this series, and now in the next videos we will deep dive into the more complex topics of quantum mechanics leading up to building the quantum system, or the examples we will see of how the quantum system is built. Thank you very much and keep learning.